morning. How's everyone doing? Can we set my slides back to the start? They seem to be at the end. It's the last, sorry. There we go. Thank you. All right. Things do not always go as planned. So good morning. I'm having terrible AV problems. There we go. Thank you. They really don't go as planned. I'm Ian. I'm a software architect at Stitch Fix, the personal styling and clothing company. I've been there for about 4 years or so, and I've learned some things about not being scared of code, not being scared of launching, and that's what I want to talk to you about today. So, when I'm not at my computer, when I'm not at work, one of my favorite things to do is go camping with my family. Be far, far away from computers, technology in general. And a few weeks ago, I was up at Moose Lake State Park. It's a lovely state park, and I was sitting in the darkness, in the night, next to that campfire, in fact. And as I was sitting there, I heard a noise in the bushes. Was it a squirrel? A bear? The lizard, the primitive part of my brain, was hyping me up for a battle with Sasquatch, while the calm part of my brain knew it was probably actually a squirrel. But that fear, little tamed fear to be sure, the fear as I stood there on the edge of the darkness was still there. And the fear comes from this not knowing, or rather, knowing enough to be able to construct mental models of potential calamities, but lacking the situational knowledge to be certain of avoiding them. Now, at work, it's statistically improbable that we'd be attacked by animals rampaging out of the night, at least for most of us. But we're afflicted by a different class of potential threats, let's say. We work with complex systems. Systems, by definition, that we can't fully model or understand. Now, as we develop new systems or expand the functionality of existing ones, we're painfully aware of just how much could go wrong. We're building something of sufficient complexity to be useful, but we're stuck with this concern that it might turn into a marauding bear when it goes live. How do we go about gaining that insight, that wisdom to move beyond that peak of concern in the dark period before launch day illuminates our work, for better or for worse? Because the fear we feel is legitimate, right? It's real. The negative consequences of things going wrong are significant. There's harm to our customers, harm to our communities, harm to our businesses, or our job security. Reputational harm, especially for folks from underrepresented groups in tech, who unfortunately tend to be blamed or judged more harshly for perceived mistakes. That fear is actualized when failures result in an inability or a lost opportunity to do meaningful things, both at work and outside of it. I'd far rather spend time with my family than at my desk fighting some bug late into the night. And the fear is also harmful. Stress is a major problem in these increasingly precedented times. Merely existing can be stressful enough without work adding more. If you look at the Maslow burnout inventory, its method for assessing burnout, it includes an entire category on emotional exhaustion. Fear, uncertainty, doubt, stress, and accumulation of worry. They're all significant drivers of burnout. Our brains just can't cope with worrying all the time. And the fear that we feel comes from the risks we perceive in our work, but the perception of risk requires context. What is at risk? What are the stakes? What are the gains we're seeking to make? How much loss can we endure if things go wrong? So in the top corner here, high risk, high stakes, the quadrant of fear. Sounds a little like a movie villain, but here we go. It's not a comfortable quadrant to be in. We often find ourselves there during incident response. We may be compelled to make risky moves because the alternatives are usually worse. We may find ourselves here when projects go completely sideways. We do not want to be here if we can avoid it. One way to move away from this quadrant is to lower the stakes. We fail in private, not in public. Fail in non-critical systems rather than critical systems. Make space for failure in our timelines and our build plans because we know that the failure boundary for our systems exists. But its exact location is difficult to discern without pushing our systems past it. And so we test, we fail, we discover, and we learn. And as we learn, we reduce our risk. We move into the quadrant of the mundane. A job is usually pretty mundane, as it should be. Low risk, low stakes is the order of the day. But as we gain more experience, more expertise, more and more things become mundane. Things that used to be risky get less risky. We build tools and techniques to reduce risk, enhancing safety, enhancing predictability. This means that we can just focus on shipping code. And the more we can just ship, the easier it is to make progress, to push the envelope, to move our projects, our businesses, our communities forwards. New feature launches, major marketing campaigns, dramatic system refactorings, these high-stakes projects without which we can't make progress, but with the risk reduced by learning. Now, different people will have different opinions on where we are on this map. As you talk with other engineers, product managers, business partners, executives, don't spook the lawyers. It's really important. They're there to keep you safe. But you can start to calibrate your exact location that everyone agrees on. It's an opportunity to synchronize your mental models of the world. What do you know that I don't that makes you more fearful? To plan a path forwards. At work, we sometimes refer to project icebergs, things that loom out of the darkness unexpectedly and put our ship at risk. Well, we don't know where the icebergs actually might be. With experience, expertise, practice, discussion, we can map and predict likely areas where they could lurk, and so together, we can chart a course forwards based on what we've learned and what we are learning through real-world experience by iterating on solutions, shipping incremental progress. Because the real world will teach us things that our development environments never could. Because the only way to learn how a system behaves in production is to run it in production. Why not just let JMeter loose, hammer on the new system, call it good? It's been load tested. But really, we need our tests to be contextual. The systems that we're building aren't operating in isolation. Other systems are all operating simultaneously. We need to be able to trace the interactions between these interdependent systems. The only way to really know how a system behaves at scale is to run it at scale. Yes, we'll have manual and automated testing to test out our products and our software, but they're not sufficient. They're very important, but they only test the things that we already know about. The test plans you write are based on your mental models and expectations, and we know that our mental models of complex systems are necessarily incomplete. We also often test under ideal conditions, whereas operating at scale reveals the odd quirks, the edge cases, the corner cases, circumstantial situations that you could never have predicted. At sufficient scale, 1 in a million happens every day, or every hour, every minute, or every second. We need that scale to reduce risk through exposure and experience. And we have to expose our work to the real world as soon as possible. In particular, we want to identify those things that concern us, those icebergs, test those as early as we can. Because if my system doesn't scale under load, then it doesn't scale and I have to fix it. If there's a weird bug, there's a weird bug, and I have to fix it. But if I learn about it at launch, I probably had a production incident exposing it. And all of a sudden, my options and my timeline for fixing the problem are much more constrained. If I found out early, I got a lot more freedom. I've got time to consider different approaches, different architectures if needed. I've got time to talk and work with vendors to sort out problems. I've got time to scrap the project entirely if it turns out it requires us to violate the laws of physics, which does sometimes happen. The question then is, how can we run a system in production at scale right now without actually launching it? How do we make the stakes low when the risks are high? And although the specifics and details will vary depending on your situation, I usually think of it as asking a hypothetical question of our systems. If I asked you to dance, would you say yes? If I ask that question and I receive a negative response, I have not actually been rejected. The question was hypothetical. But I do know not to ask for a dance. Now, a hypothetical question is pretty flimsy when applied to real-world dance partners, but much more valuable when asked of a technical system, if you follow some requirements. First requirement, do no harm. The system asking the question needs to suffer minimal ill effects from the act of asking the question. We need to be able to track the answers meaningfully. We need to know who said what in response and be able to analyze it. We need to be able to understand what happened with the question. And we need to be able to stop asking the question very quickly, very easily. This is important because while we design for asking these questions in a non-committal way, I personally am massively skeptical of any computer systems, especially of ones that I've told to do things. And I want to have an escape hatch if things go wrong, reducing risk. I want to pause here for a moment because advice like this has a tendency to be heavily path-dependent. There are certain prerequisites, features, capabilities that you probably need before any of this is actually meaningful. You don't have to be Stitch Fix, but there are some foundational capabilities that we should mention. The first is being able to make time. Most of us have difficulty with this. Certainly I find it difficult. But having time to think and discuss and plan and deliver incrementally will reduce your risk compared to working on impossibly short timelines. Feature flags allow you to control behaviors in production on the fly without having to wait to deploy. If you're not using feature flags, you should be. Monitor and trace your systems. Get automated notifications when they're moving outside of the acceptable limits. Let your systems tell you when they're unhappy. Make sure you're running automated tests with good coverage of your code. They need to be reliable and fast so that you can run them before every deploy and deploy quickly still. Continuous deployment, the ability to deploy small changes often, and the actual practice of doing so allows us to make small iterative steps forwards. Low risk, low stakes changes. Without it, we end up making large, risky, irregular leaps forward. Hopefully forwards. High risk, high stakes. And underpinning all of that, the key thing is a bright, kind, diverse, inclusive team, open and honest communication, trust, and psychological safety. You have to have good humans to work with. So the ordering of this, I admit, might be a little subjective, but to my mind, all of them are critical to reducing risk and increasing safety. All of them will add value to your projects. All of them will add safety to your projects. But assuming we've met those base needs, how might we ask this hypothetical question? So particularly when you have a service-oriented architecture with services connected by HTTP calls, a simple option is you start making HTTP calls where you would make them when you go live. But you do it with a teeny tiny timeout so that you don't significantly slow your production path down no matter how slow your new service gets. You catch everything that might go wrong, so no matter how badly it breaks down, the problem never bubbles up to your production path. And you log whatever happens for future analysis. You'll see that feature flags are there. I put them on the prerequisites list for a reason. When things go sideways, when my test turns out to be not as safe and as isolated as I expect it to be, I can stop and stop quickly. It also lets me do smaller tests. 1%, 25% of traffic, 50%. That control gives us a reduction in risk. And assuming you've set your feature flag up to 100%, you're now hitting your new service with full production levels of traffic. The new service gets a workout. We can start seeing traces in APM or stats or log lines or whatever observability we've built in. We can start learning. If not that, another option would be to put it in an asynchronous job queue like rescue. Enqueuing a job's typically fairly quick, fairly reliable, won't perturb the production flow. But the execution of your test code is then confined to an asynchronous job, which can do whatever you want it to do. How close you get to production traffic depends on how quickly you can process those jobs. If you can get lots of workers running, then you can get through it and have a very close to production level of traffic flow. The third option that I like is in many ways a variation of the second one. But instead of enqueuing a job, we send a message. This is actually a really good way of running tests on multiple different systems. You can have as many things listening to that message as you like. They can each independently start and stop doing your test at will. But we generally build new systems to do things. It's the whole point. But doing things has side effects. Doing things has impacts. It can leak outside of your test and into the real world. For example, if I start a test that reserves Stitch Fix's inventory, that inventory is actually reserved. Those clothes are not available to actual paying customers. If I do it at sufficient volume, I make it very difficult for our stylists to do their work. There's nothing for them to reserve for our clients. So be careful and thoughtful about what you write and what you do. This is my 2020 slide. Isolate. Isolate your changes in new services if you can. Keep your data in new databases. Keep it separate. Failing that, you could put it into new database tables within an existing database. Or even new columns in your existing tables, but you can see how you start to slide into a world where we can have inadvertent side effects. So data isolation like this might be easier in a more service-oriented architecture, especially with microservices, where you naturally tend to isolate things into separate domains. But perhaps you don't even need to write to your expected data store. Write some data to an ad hoc NoSQL store, to Redis or something if you want, while you explore what the final storage should look like. The great joy of this iterative development process is that you don't have to commit to specific solutions too early. You can explore, you can learn, you can play. We don't have to build solutions that we would be willing to support after launch. If I dump some data into Redis and it somehow has a catastrophic failure and it loses all of my data, in some pre-production test, it wouldn't really matter. High risk, low stakes, I'm learning. And in fact, some projects we actually design for throwing the data away. We know we're going to write junk to our data store because we haven't finished building the product. We haven't finished the system, but we want to start testing early. So we actually do build tools to let us do a big reset, like a rake task that truncates a table. When we ship the next element of the build plan, reset the data, start fresh. But, big caveat, make sure you put safeguards in tools like that to prevent you from running them after you've launched. Because there's nothing quite like dropping your production tables to really ruin your day. None of this is free. It requires thought, it requires planning, it requires talking to people, building alignment, sharing mental models, discussing trade-offs and risks. Oftentimes it changes how you go about designing and building your systems, designing those isolated data stores, building message consumers to run your tests, breaking things down into testable chunks. It has to be a deliberate process. And that can manifest in your actual project documentation. You can write down deliverables like this. When someone logs in, if this flag is enabled, we will ping the new service. This will tell us the login system can talk to us, and we can handle a load. So we've agreed a deliverable, an interface, a control, expected outcomes, and the limits of what you might discover. Because a test like that one isn't particularly dramatic. I'm just pinging a new service. It doesn't do anything, but it still has value. Also doesn't require that much additional work. You're already going to want some sort of feature flag to control your project at that point. You're already going to integrate with your new service, so you've done that. You probably even wanted a ping endpoint as part of your service health monitoring. You've got that too. It's all done. Later on, you can change that endpoint to something more meaningful, and you can do your next test. Ship, test, learn, iterate, repeat. So let's talk about some actual real-world examples to give rather than hypotheticals. Hypotheticals. So at Stitch Fix, we had a feature that involves reserving inventory for clients, and we did it asynchronously, at a time of our choosing. If things went wrong, we had time to retry and correct problems. But we wanted to see, could we reserve that inventory on the fly when clients requested it? But was our reservation system reliable and fast enough to do it? Inventory availability at Stitch Fix varies really rapidly, and so would we be able to reserve the things that we wanted to? The potential for a really bad client experience where we promise them some particular clothes and then we can't actually deliver on that promise. The risk of that bad client experience was really high. So we set up a test where the client would get that asynchronously generated collection as planned, as normal. But we'd also just enqueue a job. And that would go and ask the reservation system, if I asked you for this inventory, would you be able to reserve it for me? Not do the reservation, just would you have been able to? And we found that our fears were largely unfounded. Things just worked, error rates were low. But also, when we looked at the performance of it, we had time to do real-time error correction and stay within a reasonable response time. And that test ran for over a week. We didn't just get lucky on one particular day where we had good conditions. We had a longer-term test to give us confidence. And with that confidence, we were able to greenlight a client-facing test where we actually did this in real life and gather real-world data. But we were able to do so because we'd learned, we'd built that reduced risk. Another example. So we want to be able to recommend new inventory to new clients as they sign up. And sign-up flow is high risk. right? Any sign-up flow is generally one of the highest risk areas that you don't want to mess it up. But also at Stitch Fix, recommendations historically tended to rely on overnight batch jobs to process all of the client data that we had, go into our machine learning models. But we'd made some changes relatively recently to allow for real-time updates. But a new client, we've literally only had their data for seconds. They're in the process of answering the questions that we need them to answer. Would we be able to do it in real time? We're going to be breaking new ground. We didn't have that certainty that things would work. And so we tested asynchronously during login. Again, we just queued a job. If I were to ask you for recommendations for this client, would you have any? The answer, yes. Everything worked. We were happy. But we decided to be skeptical. What would happen if we got a big marketing push, for example, that drove a lot of signups? Sure, our system worked at the level that we tested it at, but could we push it further? Could we be confident that spikes would be dealt with? And so we quadrupled the traffic, 4 jobs instead of 1. Lots of workers to process them, absolutely hammered the system, and it passed with flying colors. Again, we were really happy, until some of our data scientists popped up, asking us, were we doing something weird? Because it transpired that down in the depths of recommendations, one of the subsystems in there had popped an alert. It was hitting its fallback option a lot more than it should have been, and that fallback was used when it didn't have client data to do its job on. So we were getting recommendations, but they weren't getting the full treatment. They weren't getting the full benefit of what we had. And sure enough, that particular system didn't support these real-time data updates. Moreover, they said, well, we hadn't planned on supporting that for a while. We're busy. It's not going to be done before you're planning on launching. So we learned well ahead of time that there was an iceberg looming, and we were able to chart a course around it. We were able to solve that problem, but we didn't have to do it after we'd launched. We didn't have to do it when the stakes were high. We also learned that our partners' monitoring and alerting worked. On the infrastructure side, Stitch Fix is relatively new to using Kafka in our engineering environments. And any new technology that you want to adopt has a learning curve. We've been able to write non-critical messages to Kafka streams to test it out, or dual write our existing messages to our current infrastructure and the Kafka stuff, so that we can learn how it behaves. And it's been working pretty well. Except, at one point, our vendor did a broker rule, adding a new Kafka broker node, removing an old one, at which point the client systems that we'd built would struggle to connect until we'd restarted them all. We found out we had a configuration problem. But this change only happens once a month. It only showed up because we had this longer-term test building confidence. Because being able to test the management and lifecycle of new infrastructure is really critical. Not just things like broker roles, but failovers, maintenance processes, upgrades, and so forth. This sort of learning can then inform engineering teams about how to design and build systems on top of this new infrastructure safely. And the other example I've got for you is these major technical migrations. So we tend to think of our code as technical debt. Right? As soon as you've committed, as soon as you've pushed, you have technical debt. But rather than thinking of technical debt, I like to think of our systems as a business's exoskeleton. To grow, we might need to shed that exoskeleton. Right? It served us well in the past, it supported us, but it's no longer meeting our needs, and we need to migrate from an old constricting system to a new one that's designed to support our future growth. Doing this can be difficult, doing it can be dangerous, but getting good at migrations like this is a superpower that will serve you well throughout your career. And the techniques that I've been describing here really come into their own during these big technical migrations. And they follow often a very similar path. You start at the beginning, you're building your new system, your old one's ticking along quite happily. And then you start writing to your new system as well, keeping the two in sync as best you can. Then you cut over, you launch. Congratulations, you're live. You keep writing to the old system just in case. And then finally, eventually, you delete the old system. You're done. Easy, right? Now, as you do that cutover, I always think of this scene in Raiders of the Lost Ark where Indiana Jones is swapping the idol for a bag of sand, trying to trick the trap that's underneath it. This is me deploying. I don't get to wear the fancy hat. It doesn't always go well. This is me in incident response. Again, I don't wear the hat. In our case, What we needed to do was completely replace the system that tracked the work that was available for our stylists and track what work they'd completed. If we completely broke this system, then we disrupt the running of the entire business. If we got it subtly wrong, it's almost worse, right? Because we'd mess up the work tracking that our stylists and their managers and our operations folks rely on. The risk was really high, but the stakes were even higher because this new design that we'd come up with would allow us to meet business needs that we knew were coming, and to do so with considerably lower engineering effort. This was our new exoskeleton that was going to support our future growth. But I described it as trying to change the wheels on a car as it goes down the freeway without the driver noticing. And the system that our stylists use is one of the oldest still in use at Stitch Fix. 10 years, one of our original monolithic apps. 10 years of growth and evolution that Indiana Jones reference. I would really need the bullwhip as I'm going down into the depths of the repo. So we've got all of this business logic that's entwined in all of our code paths. It's horrible. And the idea that we could build a replacement system and get it right was laughable. So we didn't try. We started instead with just pinging our service, just like I described earlier. Whenever we knew that we needed to interact with our new task system, we'd ping. And it exploded. Straight up tight. It was terrible. But we got a crash course in monitoring and scaling our services, right? We went and talked with our infrastructure folks. We learned about scaling. And then we taught the rest of the people on our teams what we'd learned. That's also really important. And once we'd fixed everything, it stayed up. And then we started actually creating new tasks. The data was garbage because there was no way to do anything with the tasks. They would hang around forever, but we proved that we could do it. And then we delete the data eventually. Then we started assigning the tasks. Data was still garbage because there was no way to reassign or close tasks, so they still hung around forever, but we proved that we could do it. And then we started closing the tasks when the work was done. In theory, the data was correct. We've done the whole life cycle now. But in practice, it was still garbage. But we got to learn about all of the quirks and behaviors that we'd missed. Our systems could teach us. We had a new opportunity to learn, a new step in the migration path, a place where we can now still read from the old system, but compare it with the new one. We can cross-check. And of course, our systems were not totally in sync, but every time now we could draw graphs of how often they weren't in sync. We could check the logs, work out what was going wrong, find the weird edge case, fix it, and the next time the graphs showed that we were staying in sync for longer. Every time, each iteration, we stay in sync for longer, more often. Each iteration, we find a weirder or rarer edge case and fix it. GitHub has a library, a Ruby library scientist that's very good for tracking this sort of comparison. It's well worth a look. Although it's Ruby, there's other languages, there's clones of it. It's worth digging into if you need to do this sort of thing. And eventually our graph showed that everything was staying in sync. We could make the decision to launch. And it was totally underwhelming. The car kept on driving down the freeway, the driver largely unaware of what we had just achieved. We went off to our usual set of meetings. But we kept that comparison logic going just to make sure that things didn't get worse again without us noticing. And that meant that any bugs that we had, and we did have some, would show up automatically. We didn't rely on humans telling us that things were wrong. We also had incidents during our migration. We were running for long enough that things blew up on occasion. We were fortunate in that regard because incidents are very educational. But you don't have to rely on luck. There's no better time to break your systems on purpose when no one is relying on them. A game day is a deliberate, planned, controlled incident, and we use them to practice incident response, but also to learn about the failure behaviors that our systems have. Because how we expect systems to fail is rarely how they actually fail. So make time to break your new systems. Make them time out. Make them 500. Take them down. Are your failure modes safe? Do they corrupt or lose data? Can you recover? What tools do you need to be able to intervene? Learn this before launch. Check your monitoring. Check your alerting. Because you're going to have production incidents after you launch. You're more likely to have them with new systems in particular. So taking that time to prepare means you're more likely to be able to successfully manage them. It's like having bear spray close to hand when camping. You don't want to have the run-in with the bear, but if it does happen, you want to avoid being mauled. So I've described a lot of options, a lot of work, but you don't have to do it all of the time. As William Watkinson said, it's far better to light the candle than to curse the darkness. As Terry Pratchett said, sometimes it's better to light a flamethrower than to curse the darkness. And these two scholars demonstrate that we actually have a spectrum of flammable alternatives to cursing the darkness. We got choices. We can pick and choose how we go about illuminating the unknown based on our understanding of the risks, the stakes, the time available to us, and our technical capabilities. The important thing is to have those conversations and make deliberate choices and plans to address risk. Because we seek to replace fear not with foolhardy bravery, but with the confidence, the wisdom that comes from learning. We want to seek confidence in the development process. Does what I have built do what I expect? Does it do what other stakeholders expect? Will it achieve my business goals? And we seek confidence in our operations. Does it stay up? Does it scale? Does it fail the way I expect it to? Can I fix it? Because confidence in operations and confidence in development is really what DevOps is all about. And it's why we're all here today. Thank you.